physically in the classroom. So that's fine. It's been a little bit on and off on both. It depends on the number of students in the class and the size of this room that we can find. So.
But you're going there too, right?
Sorry?
You're going there too, to the college?
Going where?
Actually, I mean like going to the college, like online and like personal too.
Yeah, I go there
Oh,
like
that's awesome.
3 days a week. I go to the U. So there's some people who can work from home just as well, like prefer to work from home, can just stay home and work from home.
Yes.
But now things are getting better.
Yes, thanks God, because here is not like that. Because like I can go to college, I just had to go there because I have a subject here is metamorphic petrology, and I had to go there to take some rocks to study here at home, but just one time. Like in the semester, I just had to go there one time because we can have classes there. Like not yet, maybe soon. I hope.
Yeah, hopefully.
Yes.
Hope so.
Yes, and the research too. Research is going. You can go there and use the lab.
Yeah.
Material. That's awesome. That's awesome.
Yeah, I mostly go there now to do use the seismic interpretation facilities, things like that, thin sections.
That's awesome. Yes, but we have also to consider that Brazil has like much more people than
Yes.
than a lot of countries, so it's kind of hard for us to control, to keep it like faster because it's
yes.
massive. It's a massive country. We have a lot of people. Yes. What we're going good. I think we are online now. Let me check here. Yes, we are online now. They're seeing here. That's really cool. Let me just wait like 3 minutes or 5 for people arriving here to welcome everybody and start our lecture here. Right?
That's cool. So how many people signed up for?
Let me check here. Oh, I have just started there on YouTube because there's a delay there. So let me check. Oh, they're checking because it had like 2 links, so there are people divided. I don't know if they are going to control it. Let me see here. People are arriving, so we have like 47 in one and 15 in another. We had like 4,000, 400 of subscribers. A lot of people from a lot of countries in the world. Really, it was really cool, really cool. Because normally we have like people from Brazil and countries that speak Portuguese, like Portugal, and some African countries, but because our lectures is all of them in Portuguese, so it's kind of hard for people to understand. But English is better.
Yeah, it's better internationally, of course.
Yes. Did you invite your students to watch?
Yeah, I did some students, and I put it on my Facebook page. So
Oh, that's good.
that should reach about
I
4,000
saw,
or 5,000 people.
I saw that. Yeah, it was great.
So we'll see. Yeah, we have a few Brazilian students here too in Bergen. It's
Really?
like 5 that I see every day, more or less.
Is there an international university or like national?
It's a national university, but it's a
It's mixed.
international environment. So that's nice. Yeah.
That's awesome.
So
That's
it's
awesome.
great to have some Brazilian students around. That's cool.
That's great. That's great by now because it's getting hot there also, huh?
Here,
Yes.
it doesn't get hot here, but it's not by Brazilian standards.
Yeah, for sure. Not that hot.
A few days a year, not
Yes. Yeah, I could imagine. Is as our cold time here too. We just have like cold weather like for 2 weeks, 1 year. Like for me, like right now it's not cool. It's cold, a little bit cold because I'm inside my room. So, but it's a little bit cold outside. But for you, it's like really cold.
Cold
Yes.
is like 15 degrees or
no, 15 degrees for me is like freezing.
okay.
15 degrees is like freezing. Like I mean Celsius. Celsius is yeah. No, 20 degrees. I think like everybody's like, oh, it's getting cold. 20. 18 is like, oh, 18 is cold. It's cold. You have to wear a jacket or something like that. But I mean, like I'm talking about Rio because Brazil. There's like the south part of Brazil is like it goes like below 0 sometimes.
Yeah.
They're more used to
18 or 19 here today, and it was really warm.
Yes. Yes, I know. Cold for you will be like much more than below 0.
Yeah.
Yes. Let me take here. They're saying first that people is arriving, so we can wait like just a little bit to start.
Yeah. That's great.
And just like curiosity, how is the like a field work in Norway? I use it to like to have a trip around the country.
We do that. We also go to. I mean, we've had several trips to Brazil actually over the last
Really, that's awesome.
years. We don't have any one on the agenda right now, but then we go to the Petroleum Geology field courses run in Utah, United States. That was not possible this spring. It was not possible, unfortunately. So Had to do that
Yes.
remotely.
Yes, but like with the students from the college that are graduating, you also go to another countries too?
Yeah, we go to the U.S. every year.
Oh, that's
That's
awesome.
that's
That's great.
graduate students. So graduate students.
Okay.
Undergraduates go to the Mediterranean, to Elba, for a couple of weeks of field course,
Mm-hmm.
and then there are trips, of course, in more locally in Norway.
Mm-hmm. Oh, that's great. Yes.
There are
You,
lots of exposures just around the university, which is nice.
mm-hmm. That's great. Yes. Here I use it to go to some states, to like different states to the south or to the southeast, that where we live here too.
Uh,
And we go at UERJ, at my college, we go a lot to Minas Gerais. It's a state
yeah,
like a little bit close to Rio, and there's a lot of geologic things,
yeah,
like great things to see
I know.
there, to
Yeah,
learn. Have you ever been there?
yeah,
That's
and also
awesome.
in Rio, there's also some nice outcrops and Cabo
Yes.
Frio, and especially Cabo Frio is
Yes.
nice. Many
Mm-hmm.
places along the coast. Yeah,
Mm-hmm.
so yeah, that's
Yes.
great.
It's like a outside school.
Yeah,
It's like an outside school. So they said like there's almost 100 people watching us,
great.
and I think I can start. So let's go. Hello, everyone. My name is Davi Atanasio. I'm the treasurer of AAPG, the student chapter of UERJ, the State University of Rio de Janeiro. And here we are today with Haakon Fossen, one of the greatest geologists in the world. And great afternoon to everyone. Actually, great afternoon to everyone that is watching us from Brazil, because there's a lot of countries in the world watching us. And let me tell you a little bit about him. So, Haakon Fossen is a professor at the University of Bergen, Norway, in the field of structural geology and tectonics. With a PhD from the University of Minnesota and experience from exploration and field production with Statoil prior to joining the university, he has a wide field of interest and experience. Haakon Fosse is actively involved in research on subseismic faults and deformation bands, faulting, rift evolution, shear zones, transpression, tension, tectonics, structural inheritance, orogenic processes, and extensional collapse of orogens, and is interested in processes that range from microscale to that of plate tectonics at any crustal level. Most of his work is field-oriented, with a currently focus on the North Sea Rift, the Scandinavian Caledonides, and the Brazilian orogenic system in Brazil. He has authored more than 150 scientific papers, several books, a book chapters, and is the author of the international textbook Structural Geology that I think everybody here knows, and Cambridge University Press, that has been translated to several languages from Korean and Chinese to Portuguese. So, welcome, Haakon Fossen, to our YouTube channel. It's a pleasure for me and for my whole chapter to welcome you here. And I hope we can all learn a lot with you. I hope we can share content, and I hope we can have a good lecture. um, just saying a little bit, like some tips here. We are going to have a time in the end of the lecture for questions, and I'd like to ask you, please, to ask the questions in English, because there's a lot of people here that don't speak Portuguese. So it would be easier for us if you speak in English, please. And this lecture is going to be recorded, so you can see these on our YouTube channel. It's going to be available there. And yes, okay. To those who are interested in a certificate, we are going to put a link on the chat. So please just click on the link and fill the link there, and we are going to send the certificate by your email. Okay, like it's going to be available till 30 minutes after the end of the lecture. And yes, that's all. So let's start. Welcome, and let's start. I'm going to
Thank
be
you.
here. I'm going to be here. Okay, if you need, I'm going to be in the background, and that's all. Thank you for the opportunity. Really appreciate it.
Thanks for the nice introduction. I'm very happy to be here online and for being invited. It's always nice to be invited by students. I mean, students is the future, right? So that's well invested time, you know, talking to students. I like that. So
Yeah,
thanks
right.
for that. And I guess I can just start, right?
Right.
I will
Right.
start my presentation, and you tell me when it's showing on the screen.
Okay. I can see a screen. Yes. Perfect. So I'll be here in the background. If you need something, just let me know, right?
Good. Yeah, very good.
Okay, thank you. Have a great lecture to everybody.
Thank you. So yes, so I was asked to talk about extension, petroleum geology, this kind of part of geology. So that's what I'm going to do. I'm going to say a few things about crustal extension, petroleum geology. The extension is illustrated here by this very simple cartoon that comes from one of the e-learning modules that you can find online on my website or Cambridge. And we're going to talk about what a rift is and a rifted margin very briefly, and then look into the details. We're going to talk about rift evolution, the way rifts form at a large scale over time. We're going to talk about structural inheritance, so that's pre-existing structures that influence rifts and the way they form. And transfer zones, accommodation zones, that have many names. And I'm going to talk about the way that faults grow by linkage primarily. And we will talk about faults at a little bit smaller scale, the complications and implications for communication. By that I mean fluid flow, basically, sealing, things like that. And end up with a few slides on subseismic structures. So we go from very large structures down to the millimeter scale or less in the very end. So the picture in the background is from some nice faults in Chile, near Antofagasta. And what is a rift? Well, all of you know that, but anyway, we start from there. It's an elongated region of crustal scale extension and lithospheric thinning. So you extend, you stretch. That's what these blue arrows here indicate, right? Sort of tectonic stretching. That could be related to something much bigger than the rift. I mean, we know plate tectonics, and this, you know, everything is connected globally in a sense. So you have plates moving in different directions and different times, and that's the tectonic contribution. And then there is the sort of the vertical upwelling of hot mantle material that could also be quite important during rift initiation. And it's like passive and active tectonic explanations of rifts that both are, you know, relevant and active in most cases. So the doming stage is often referred to in the beginning, and then the rift develops in very simple terms here with its different faults, and then it becomes a basin. The crust is thinned, the entire lithosphere is thinned, and there's also indicated what's we're going to call a transfer zone here in the middle. So structural variations along strike in different segments of the rift. And eventually, what people call a successful rift is when the rift is sort of, the crust breaks and moves apart, and an ocean forms. So that's sort of when you form passive margin. So a passive margin would is the result of rifting. So they're often called rifted margins too, for that reasons. And most hydrocarbons are stored in in the maybe a little bit more in passive margins and some in the rifts actually. come back to that, I think. In terms of offshore Brazilian continental margin, we hear the pre-salt often referred to, and that's what we call the synrift here. And then we have the post-rift sediments, synrift sediments. And then we have all the faults here and the slope, and then we get out into the oceanic basin with oceanic crust. So that's sort of the end of the rifts, and things get passive, and that's what we call the passive margin. Passive margins along the passive margin of Brazil is very famous, and it shows this variability that characterizes most or all passive margins, actually, where you have some very narrow, some very wide, like the Santos, and some very different structural geometries along the margin that relate to the rifting, and especially the last part of the rifting just before breakup. Very exciting things, these variations, and things that start with rifting. So yeah, so okay, it's kind of rifts and rifted margins contain more than 50% of the world's petroleum resources. So these are very important in terms of petroleum geology. You want to understand how rifts form and the dynamics and everything about rifts, so that you can put your effort in the right places and put your wells in the best possible locations to find petroleum. So that's why it's important. Oftentimes, when we start with the evolution, or sort of the beginning of extension, one simple model, and it is not the only one, it's a simplified one, is that you start out with a widespread extensional deformation with lots of faults spread out, like shown in this figure in A. And then over time, some of these, as we will see, link up and form bigger faults, longer faults with larger offsets, displacements. And they end up with some kind of network. So these other ones, the other small ones that are not so lucky, they will become inactive, and some of them will grow into big faults. So you establish some sort of large-scale fault blocks at an early stage, and that's sort of the main faults and the main fault block, so architecture of the rift that is then established. And we can go, for me, it's natural to go to the North Sea Rift, which is just west of southern Norway, northwest of Great Britain. This North Sea basin between, where we have some nice data now. We've been dating faults onshore, and we see that they form at an early stage of rifting, very early stage. We have small faults in a very wide area. We can see them going far into the margin, the current margin, even onshore margin. This is from dating these faults using clay gauge minerals, illite, and potassium argon dating methods. So we can show that we have this initial small-scale faulting sort of beginning of extension, and then over time, some of the faults grow into larger faults, but not in the whole extended area, the whole area that was extended, but in a smaller part, and this part becomes the rift then itself. So these early faults are then left on the shoulder, many of them inactive. Some of them could still move a little bit, but the main extension is now taken up by what is defined, what you can find as a rift from where you have larger faults. And by larger faults, I mean kilometer size offsets. And then you get sediments in this basin, you develop a basin here. And In the North Sea, this happened twice because you have two phases of rifting, a Permo-Triassic and then a late Jurassic mostly phase. So you fill up this. So that's kind of, it seems to work to some extent, this simple model of that we see here on the right side of the screen. And laterally, the rift also moves. And you can think of a rift moving and also the ocean following the rift, like a sort of a zipper style, so that you unzip a continent from one end to the other, or from two sides at the same time, often, like in the South Atlantic case. So I have these maps here on the right indicating South America on the left and Africa on the right, and the rifting that starts. And you can see already from this 140 million years reconstruction, which is taken based on Heine's work, 2013 publication, redrawn. The rifting starts here, and then it propagates northwards, right? And most of you know this, but it's quite a nice case. And just like a zipper, so then the ocean sort of follows, right? And it moves up after the rift has done its work and prepared the crust for the ocean to enter the sea. So that's kind of overall is sort of a zipper mechanism. But then it's not that simple when you look in details. There is, for example, the complications around Santos and the Florianopolis fracture zone, Santos Basin. It doesn't break into an ocean very easily. It takes time. And before that happens, you actually get ocean up here to the north. So it's like you have a button here. So that's more like also like, this is my shirt. I took a picture of my shirt today. There are buttons here. This picture, there's one there and one there. There's one here, and then this one here was opened before this one here. So that's, oops, sorry. So that's a little bit like what we can think of this as, opening irregularly, not sequentially, the buttons, and then you get this kind of complication. So that's kind of a nice analogy, I think. So the point here is that the rift and the rifting sort of propagates laterally in most cases, in all cases. And then you form the rift, and the rift there's not two rifts that are copies of each other, of course. They're all different, and they vary along strike as well. But there are some sort of classical things. One of them is that the rift shoulders and margins, they are cut off by a fault, a big fault usually, which is sort of the bounding fault, or sometimes called breakaway fault if we have sort of detachment systems. And then you find in the rifts sort of grabens and horsts, not so deep, so maybe we will call these a sort of platform area. And these highs are very interesting for petroleum geology purposes, and in the North Sea and some other places too, actually find oil here in the basement, in weathered and fractured basement, in addition to what we find in the sediments. So here basement can be very high. This figure doesn't show the sediments. It's generally mostly the basement, the way it's deformed, that is exposed here in this figure. Then you have this sort of typically terraces that takes you down to the lowest part of the rift, sort of the central graben. And oftentimes also we see what could be called domino complexes of faulting, and where all the faults are dipping in the same direction, and all the fault blocks that they define are rotated in the same way, right? Rotated like this. So it's like bookshelf tectonics or domino tectonics that you find in many parts of most rifts. Platform again, and then you get to the other rift shoulder and the other bounding faults. So there are different. So some of these portions are rotated, especially the domino complex here, and other parts are not much rotated at all. So that's going back to realistic actual cross section. This one again across the North Sea rift. The Viking Graben is the name of the central graben, and rifts are not symmetric. You can see this has this like the domino complex here on this side, the horst in the middle here, and so on. So there's different styles and these styles change also along strike. And then this is onshore. This is where I am sitting right now. The rift is offshore. Here's the main bounding fault here, and there's another one on the other side. And then, like I said, these faults onshore in this region, for a large part, were active at an early stage before you actually formed the rift with all these structures that we just talked about here. Another thing is that if you look at these fault blocks, the width of these fault blocks, the distance between the main faults, there's sort of a regularity, right, between these. It's like, there's a scale here, scale bar, maybe 20 kilometers, 10 to 20 kilometers or something like that, somewhat more. It depends how you define a large fault, of course, but there seems to be a regularity, and we find that actually at all scales that spacing of faults in not only rifts but many other layers. If you have a relatively stiff layer like the upper and middle crust, or in some cases the whole crust, there's a relationship between the thickness of that layer, thickness of the brittle crust, and the spacing of these. Like taking this figure from a colleague of mine, Crustal Soliva, who published this, we can see that the layer, there's two layers here. There's one layer, this is one layer, rigid layer, and then there's a weak blue layer, and then there's a new rigid layer. So this spacing, and spacing is the distance between these, is related to the thickness somehow, to some extent. And in many cases is very roughly half the thickness of the brittle layer. Right. Let me show you a picture at a much smaller scale. This is series of cemented sand layer with shales in between. It's from the Cocosí basin, a small basin up in the northeast of Brazil, the Borborema. And some of you may know about that, some of you not. And you can see these are the competent layers. For example, this one here. And here's a fault here. There's a little fault here. There's a little one here, and so on. So there's kind of a regularity here of spacing. This one here. And sorry, if we go to this layer down here, it's thinner, right? It's this, and you can see how this the spacing here between these faults. There's a little fault here and a little fault there. There's another one over here that is a little bit bigger than these small fractures. It's a little bit smaller than the spacing up here. So this is quite a nice relationship. That, of course, this is not completely. It's basically by observation. It's not really calculated. But this sort of can be applied at very different scales. So there is a 1 real here for scale. So that's something interesting, because these first order faults and rifts are very important because they can create very significant traps with hydrocarbons filling up the top of these structures. Okay. So what happens at depth? So we see these faults, and that's oftentimes the case. We have good data of the upper part of the rift, seismic data, well data, and so on, but we're not sure what's going on deeper down. So there are different models, and the classical models is sort of the symmetric, the pure shear model, right? And then there's the asymmetric simple shear model. The reason why it's called simple shear is this sort of detachment / shear zone at depth that controls much of the extension. It controls the hanging wall fault blocks that we see here, and the way that the heat is distributed, and many other things. The basin maximum depth of the basin here, and so on. It's very asymmetric. Of course, these are idealized models from the 80s, but they are still good sort of end member models. So that's up here. We have more what's called a pure shear, right? So you just stretch the whole lower crust and also the upper mantle, the lithospheric mantle, in a more homogeneous way, without forming discrete detachment shear zones or faults. This is a field example. I'm going to use some examples from Brazil here. So this is from sort of rocks, a granite deformed at brittle ductile transition, and you can see the brittle faults here, here, and here, and then the more ductile material underneath, which is actually an ultramyelinite, but that doesn't really matter. The point is that there is a difference in rheology, in mechanical property, between this lower flowing rock and the upper sort of brittle breaking up rock. Oops, what is going on? Oh, I see. Sorry about that. When we look at seismic lines that image most of the crust, doesn't image all of the crust, it's about 20 kilometers down here to the bottom, we can see something very similar. We see these faults here, and there's a fault here, and I don't have permission to show very detailed images of this, but it's good enough. And then we can see this stuff down here, which is much more reflective, and it looks like we have like a fault block here. Top basement is about like that. Another one here, and another one here. So it starts to look, it's another fault here actually. It starts to look very much like what we have in this small picture. This granite is actually from the south margin of the Patos shear zone in the Borborema, but it doesn't matter, just to tell that I have some Brazilian examples here. So this, of course, has to do with how the crust behaves at different depths, or more precisely at different temperatures. Now, this figure on the right, or lower right, shows how a fault in the upper part of the crust, this is the surface, supposed to be the surface up here, changes character as we go down, and especially through the brittle plastic transition of quartz. Quartz starts to flow to dynamically deform, the dynamic pool crystallization, and so on. And feldspar down here. And then we, in simple terms, get into a situation at deeper depth where we have more of an anastomosing shear zone system, and not so much a single discrete fault. So that's what may be going on down here. right? So in some cases we think we can see exactly this transition on the seismic data. This was the transition at the time of faulting, not necessarily today. And this is just the same thing here on the lower left. It's from an old paper by Brun and Chaucron, or something like that. The pronunciation is not perfect, my French, which shows this sort of domino, but very large scale in our case, because we're looking at the entire crust. Here are this section that we just looked at here with the sort of base of the brittle blocks here. Actually, we had another one here. But then in the same rift, we also see the other way that the crust deforms, which is by detachment faulting, detachment style faulting. And this seismic section here is from the same rift, just a little bit farther north. And there is a sort of a detachment, it flattens out. We don't see this pattern, and on good seismic, we can see how this flattens out and then cuts through the crust. So going back to this paper from 1983, we have both of these. The décollement, I mirrored this because I wanted to match the seismic line. And we have this sort of domino style non-detachment deformation that we see here. Both of these we can see in rifts like the North Sea rift, and both of them are important. And the detachment style is something that oftentimes develops at a late and mature stage of rifting, more than at early stages, which we will come back to. So that's an important thing, that on seismic lines, here's the MOHO, this is a drawing of a deep seismic line, we see quite a reflective pattern in the lower part of the crust, underneath the well-defined faults that we find in the upper and middle crusts. So it's hard to know exactly what that pattern is, what is causing that pattern. But as a structural geologist, I like to think that many of these are shear zones. And that's what many other people think too, that we have shear zones and networks of shear zones, also different metamorphic rocks that create reflections. This was discussed in the 90s quite a bit. This paper from Blundell, so why not use the old papers, where they actually put this model here that we see on the left into computers or that's generated the seismic response using different velocities and densities of these rocks in this model. So it is, they found out that at that time it is possible to create this kind of seismic patterns from realistic rock variations in rocks and fabrics. Here's another example. We're going a little bit south of Brazil to the same margin where we have a rifted margin. This is more or less mostly a volcanic margin, but it doesn't matter. In the lower crust here on this seismic line, it doesn't show up so well here, but you can check the papers by Clark and others from 2015. And the MOHO down here, we can see more reflectivity here, and they actually sketched it out for us to make it more visible and blew it up, zoomed in here, and this is the pattern, and it looks very much like a pattern of shear zones. And here are some details of the seismic expression. So what do patterns of shear zones at this depth look like? We don't have to go so far. Having Rio as our starting point, we could go to many places, but a good place to go to look at things both in the field and from geophysical data is the Borborema province in the northeast of Brazil, where we have very beautiful shear zones. The Patos shear zone here, another shear zone down here, the Borborema shear zone. Whoops, it's going to go up here. And other shear zones in between, forming a network. And this network we put into a program that can mimic the seismic image that this would give. We would have to turn it vertically, and then we got this. It depends. I mean, there are many ways you can do that. You can change different parameters, frequency, and so on. But it's not difficult to create a pattern from this kind of shear zone networks that look very much like what you're observing on seismic data. So this is about the lower crust. There is a good chance that it's a lot of shear zone network in the lower part of many rifts. It's another beautiful picture, Google Earth, actually, from the Patos, the west-east part of the Patos, with this sort of nice lensoid sort of, geometry is a little bit more up like this, that dominate shear zones here. And very similar to what we see. Of course, you don't have to go all the way up there. You could just go to Cabo Frio, and Julio will show you nice shear zones there if you ask him. And the thing is that these shear zones, once they form, even in the same kind of rock, you form a completely new fabric, a very strong fabric, and a velocity and isotropy. So the sound moving, or the seismic waves moving in different velocity in different directions. And this, in itself, may be enough to create seismic reflections. And then if you have lithological differences at the same time, you should be able to create this kind of seismic reflectivity that we see on deep seismic lines. But it's not only shear zones, we have to admit there's also many rifts and rifted margins that are characterized by sills and dikes, intrusions and extrusions. And these sills in the lower crust, they have to be deep sills. We think that they may look like what is shown here on this line. In the field, we find many examples of this. For example, these are from the East Greenland margin, where we have a volcanic margin, and they could also give reflections, but they would probably be a little bit different. I'm not going to talk more about that. That's enough about the lower crustal reflectivity. But we're still going to be down deep and look at the connection between shallow and deep deformation. I like this section here. This one is from the Iberian margin west of Portugal, west of Porto, the town Porto, and the Galician Height. This is all the way west, close to the ocean crust transition, but there's still crust here in this part. So we put on some interpretations from a paper by Limer and others, recent paper. We have the faults, sort of domino style. And then if we go back to just the seismic, we have a very, very marked reflector down here. We can trace something like this, and it goes on and goes on and goes on. And then we have these on top, these faults here. So I'll just put on the interpretation, their interpretation. It's a little bit different here, but it doesn't really matter. These faults, these are basement blocks. This color is basement. And then there are the syn rifts, mostly sediments here, in these colors. And this up here is the post rift that was deposited after rifting, when rifting ended. We've got subsidence. But that's the point here, is that detachment. It shows very nicely that detachments exist, and they are very conspicuous, very long, and probably very important for the way that these form. And this is a high strain situation. There's a model, I mean, that looks very similar. This is a model by Brun and others they published, where there is such a display, such a detachment. And I will just trace that out for you so you can see that detachment is more or less like this. You can trace it all the way out here. Then we have things breaking up, but it continues then on the other side. It's actually folded down like that and back. So very, very impressive detachment that controls the faulting in the middle upper crusts above it. This detachment actually, it starts out in the continental domain, but then so here's the crust's mantle boundary is right here. So the mantle actually is the footwall in this western part of that section. So since we have an experiment here, we can look at how that developed. And that's quite interesting. This is a nice paper that shows the early stage here. So in these figures, the red faults are the active faults at the different times. So this fault, this is an ordinary, it's not a detachment at this point. It's a normal fault, but it cuts through the entire crust and even into the mantle. And it does that because we have a relatively strong crust and a strong upper mantle. These are the parameters that you set at when you make an experiment, and things become different depending on the rheological stratification profile of the lithosphere. But that's what we have here, and we produce this fault. It's nice, and with some antithetic faults here. And then you see after 8 million years, it starts to become more low angle, and now we're looking at something that we could call a detachment. And it's active. At some point, it becomes inactive. It first produces these, as long as these, they don't show the whole history here, but these also form in between these two stages. And at that time, this is still active. At some point, it becomes inactive. More or less, there has to be a little bit of activity, I guess, to stretch this out. And this margin is stretched pretty wide, more or less like the Santos or Angola basin in this figure at the bottom, which is supposed to be an analog. And you end up with this situation, exactly what we had here. It's very long detachment fault, and then the block faulting above it. That again, are the width of these are related to the thickness of the crust when they initially formed. Now the crust here has been thinned. These have been pulled apart a lot, so you have to restore these to the initiation of these faults to make that relationship work. So yeah, so important. In addition to the detachment itself, there are two important things to think about here above the detachment, and that's the faults and fault block rotation, which is quite important, and fault activity. Were all these faults active at the same time? When were they active? Or how did that work? How did that develop? And this model here that they published doesn't show the detail regarding the timing of these faults. So we have to think a little bit here. How did that happen? So then we can go to, and I like to do that, go to very simple physical experiments. Sorry, there's a Norwegian, but you can understand the gypsum plaster, and there's plaster filled in the box, some markers on here, and then we pull one side and we create faults. And the interesting thing here, at least one of them, is that you start out by forming one fault. It's interesting. That's what you did in the other one too. You start up by making one big fault, and it develops down here. Then it's not that big, actually. The displacement is not so impressive, but it cuts through the whole thing. But then that becomes inactive. This fault here is the one that we can see here. It gets deformed a little bit, because what happens next is you form a new fault back here. It's actually this one here propagating from the bottom up. And that becomes actually bigger before that one too becomes inactive. And you start to form a fault in the footwall to that second fault. Now that's third fault here. So this will be fault number 3, fault number 2 and 1, right? That is interesting because that actually develops into a detachment on top of this barite sort of basement. And then as you pull this out, there's a relief forming, which is also what happens in many basement, top basement surfaces during rifting. And that becomes almost horizontal here, and it ramps down like that, deforming the hanging wall blocks. You can see how nicely it's deformed. You're forming a horsed here, a rotated block here, and so on. So if somebody gave you this last image here and told you which of these faults formed first and last, or did they all form at the same time, active at the same time, which maybe is what most people would guess if you didn't know better, then you could actually say no, based on this experiment, that they actually formed one after another, mostly. And not always in a progression from one side to the other, but in this case, there's a large of that. And then you get this one here, which is not in the footwall to that blue fault. But so that's quite interesting. These faults did not have to form at the same time. They didn't have to form, they formed during the same rift event, the same extensional event. It was continuous extension, right? Progressive deformation, but they had different lifespans, different portions of that rift event. I have an experiment like that just to see what kind of stuff we're talking about. This one, unfortunately, doesn't have very good markers, but you can still see what's going on, I think. Let's run that from the beginning. So this is what we do. We just pull one side, right? And we form a fault here. See that fault? And then we form a fault in the footwall here, and that becomes a detachment, low angle. This one doesn't move anymore. And then we get a new one here and one dipping down like that. That was a little bit fast. Let's see. We can do that again. Oops, I'm sorry. No, that doesn't work. I was going to stop it. Right. Let's go back one more time. First fault forms here. It's similar to the one we looked at, the drawings. Then the second one back here. And then a horsed sort of thing here. And then this is the last one to form. And now this last and the biggest fault, or at least a very big fault here, the last one forms in the middle of this sort of extensional experiment, or rift, if you like. That's okay. And this is just to show, this is a section, this is the moho down here. So it's a whole crust. How you get these images, right, from rifts. And what we see is the end result of a history. And it's always important to think, how did this develop? So was this fault here, when did that develop? Did it develop before or after this fault? And we can see there's this sort of detachment sort of geometry of this. There's a horsed here. And in rifts, to deal with this timing issue, you apply, you look at the basin fill, and you see this kind of wedges in here, like this one here, for example. If you know the age of that, then you know that the fault moved at that time that was deposited. This here, and this one, green one here, is mostly post rift, and then you got a new phase of rifting on top of that, which complicates things in this this case. I think this one here is actually the youngest big fault, which then rotates all of that portion to the right and form these faults here that we can prove were relatively late. So that happened in response to that. So this is actually the last fault here, which is a bit similar to that fault, which is the last one to form in this model. So this thing about looking at the sedimentary evolution in different half grabens or different parts of the rift is important. It's not always easy because wells, there are a few wells. There's actually no well that penetrate any of these orange or yellow that is shown here. Maybe one locally. It's mostly, petroleum geology. They are concerned about the upper parts. Down here, things were probably too hot, or there's things migrated away from there, so I'm not interested in that so much. Another example, this is also from the North Sea rifts. And when I look at two faults, one is called the Øygarden fault, it's this fault here. And the other one is the fault that you can see here, it's called the Vette fault, it doesn't matter. Now, if you look at the hanging wall, this is top basement, the gray non-colored part is basement. If you look at this sequence here, Triassic sequence, you can see it's much thicker here in the hanging wall to this Vette fault than to the Øygarden fault. And if you work out the seismic stratigraphy here, we will find that there's a sequence here that was deposited before this lower part of that hanging wall filled sequence was deposited. So this has an older history. This Vette fault was the first one to form. You can put a 1 here, and then the Øygarden faults formed and moved. In this case, they then moved together during the last part of the history. So this fault 1 was not inactivated in this case. It was still making space for sediments as this one was moving. So a little bit different from what we saw in the experiments. So then we have a history here and the nice thing is that if you look at the top basement here, it's fairly straight here and it's fairly rugged up here. And this is an old topography that is related to footwall uplift of that fault. And you can actually look at that topography in 3D and you can create a topography, sort of a map or a 3D illustration here with drainage systems that represents the topography at the time just before these sediments, they were covered by these sediments. That will be in the Triassic. So these are Triassic mountains forming in response to movement on that fault, what's called footwall uplift. So not only the hanging wall goes down, but also the footwall moves up, not as much as the hanging wall going down, but still significantly for large faults. So I made this figure for a paper that we're working on. It's not finished completely, but it's maybe a little bit confusing because it shows the first part of the history here. So we had the two faults, right? The Vette fault and the Øygarden fault, but the Øygarden fault didn't exist at this time. So there was this fault here moving, giving space to unit 1, and then there was an uplift here of the footwall, and that uplifted basement was attacked and eroded, and we got this landscape, which was then buried once the Øygarden fault here started moving. And this was still moving, but the whole thing was moving down because of the offset on this fault over here, so it was buried. And this beautiful landscape here with mountains about 800 meters high, were preserved under the later Triassic strata. So that's so this basin fill stratigraphy and evolution and geometry is very important. Why? And the fault, so it's very closely related to faulting, right? The facies, where you have coarse grained and fine grained, and different transport directions controlled by these rotated fault blocks. And so the faults create these footwall uplifts, create basins on the other side. And so we talk about source, the mountains are being the source, and the sink being the basins here for sediments. So that's important for exploration strategy and production management, to understand these systems, how the interaction between tectonics and sedimentation works. Here's taken from some other people, how you can have small basins developing into much bigger basins, and then you have sort of a different history here that would be interesting to understand and know about when you're exploring for hydrocarbons, for example, or just trying to understand a rift and the way it evolved. And it's nice to have some Brazilian examples. This is an example from the Borborema again, the Rio de Peixe Basin, Fish River Basin up there, where we can see very similar things to what the upper figure shows, half grabens bounded by faults. You can put in the sediments here, the basement is underneath, and these are the two faults shown in this well-known seismic line. And in here, there's stratigraphic variations from more coarse, close to the faults, conglomerates, coarse Arcosic sandstones, to more fine-grained facies away from the fault, just like we see in this upper figure here. Just another figure showing more or less the same thing, the importance of understanding the structures when it comes to predicting where we have different kinds of sedimentary rocks and how they formed with alluvial fans from the cliffs here, and more axial transportation, rivers in this case, along the middle of these smaller scale grabens, half grabens mostly. I'm not going to spend a lot of time. This particular figure relates to actually two detachments, but that doesn't have to be the case. But whether you have a detachment like this one here or not will influence, of course, how these fault blocks will behave, how they form, which ones are uplifted more than the others, or will be higher than the others and produce more sediments. So all of this is interconnected. Understanding the structural evolution and the structural geometry of a rift is really important, even at depth like this. And this is in the crust, right? For what's going on at higher levels. So that's a very important point. I don't want to skip that, spending a little too much time maybe. So one point that I mentioned was rotation. So this was the timing that we talked about a little while ago, about which fault was active when relative, to the others. And in the very simple, this is just a very simple bookshelf model, domino model. They are all active at the same time. If you move books in your bookshelf, they will all move at the same time. So, but it's not that easy in reality. The point here with this figure is that when you find a domino system like this, and the bedding is dipping like in this direction and the faults in the opposite direction, then you want to restore that. And when you restore things, you want to restore bedding to become horizontal, like down here, and then the faults become steeper, obviously, right? And that's also very important to understand, that relationship between rotation of bedding, of beds, and paleosurfaces and rotations of faults. Because we know that faults, they form at ideally around 60 degrees, maybe a little bit more, and then they rotate, so we can restore things. That's definitely something we want to do. And when we do that, we find that the length, right, the length of this, it's not very straight, it should be, the length of this section here is now much shorter. And when we have this change in length, we talk about strain and extension of beta factors. And that's something that we should do if we work in a rift environment. And then we have to restore. In this example here, it is very simple because everything is horizontal. So we just put things back along the faults and we measure the extension. In case of dipping beds, we have to do some rotation before we actually measure the extension. And the extension, we can also just measure from the faults how much a reflector or a bedding surface has been moved. And if we look at the horizontal component, we talk about heave. It's called heave, right? And throw is the vertical. So heave summation is something that you will hear, just summarizing the horizontal movements. So this distance here, horizontal distance between these 2 points, for each fault in your section. And you sum that up and you find the amount of extension in that section between 2 points that you have to define. It could be the sort of the master faults at each end of the rift, for example. And when you do that and compare it to sort of crustal balancing, and by that I mean that you have an idea about the original crustal thickness, and then the crust after rifting is thinner, and then you put back the crust to achieve that original supposed thickness, then you will get, this is different answers. And that's interesting. This is a well-known sort of challenge in rifts especially. So here we do that. We first do a heave exercise. So we summarize the heaves. This rift has 2 phases of extension, but it doesn't matter. The first one is 30 kilometers, and the second one 20 kilometers if we believe in heave summation. And that should be 50 kilometers altogether from the start of rifting, which is here, and to the end of rifting, which is this upper one. 50 kilometers of extension. If we do crustal restoration, and that's taking the basement and putting it, squeezing it back into a box here. So this box would then have thickness of the crust prior to rifting, which we don't know, but we can infer that from the margins, right? The thickness of the margins that are not affected by rifting. And then we always get a higher number than if we summarize the heaves. And in this case, we almost get the double, 96 kilometers. Of course, it depends on the interpretation, the way you interpret the moho and so on, but usually it's always bigger. So why is that? What is going on? And this was discussed in the 90s a lot. And people realized that there is a contribution from faults that are too small to be observed. And in a regional section like this one, you only pick the largest faults. There's a lot of small faults that you could see from more high resolution 3D seismic data, for example. So then you could add those. And we know that below that scale, there's also small faults that you would never see on seismic data that would have a contribution in terms of, between these 2 points, there would be an extension, right? But you also should summarize, and even between these even smaller faults and so on. And it turns out that for each big fault, there's many more smaller faults, and I'm not going to go into this, but this kind of arguments indicate that that there is a significant contribution from small faults, and it may well be 40 to 50% in cases like this, where we are looking at very low resolution regional deep seismic lines. So that is, I would say, the main reason. And then some people, especially where the strain is high, because when strain is high, you have a lot of rotation of the original faults. And that's what this cartoon is supposed to show, that you have the faulting originally at the top. And then these blue faults rotate. And when they rotate a lot, till 30 or 20 degrees, you're likely to get a new set of faults that cut through the first set. And when that happens, it's the new set here that is really what catches your attention. And it could be very difficult to identify the older faults, which I know could very well be horizontal or subhorizontal. So some people say that you're probably missing some faults, especially low-angle faults that have been rotated and cut by younger faults. And the contribution from these old faults, rotated faults, should be added, or that explains some of that discrepancy between heave summation and crustal area balancing. So that's about fault rotation and strain a little bit. Let's take a breath, something to drink, and look at another very important feature of rifts. Now back at the this was large scale to a large extent. So large scale, this is, as you recognize, the East African rift system. What is the influence of basement structure, the structure that was there before rifting started? The shear zones and faults and foliations and fractures, whatever, in the basement, and lithological differences and zones and so on. And it is easy to show that it has some influence on rifting, on the locations of rift and the geometry of rifts. And this is the famous example from East Africa, the East African rift. This is from a paper by Tomasi and Borges some years ago, where they put in the foliation in the basement. So this is the white lines here are the old foliation, pre-rift foliation that we can map in the basement. And you can see this is the Tanzanian craton right here with little foliation, and it's strong, right? You can see how the rift, when it gets, if you imagine it propagated from up here or from down there, it hit this craton and decided to go around it, maybe from each side, on different sides of this craton. I'm not sure exactly how that developed. The point is that the rift is very much influenced by, follows the foliation pattern here, basically, and here. And you also see some shear wave splitting an isotropy here, which is related to differences in velocity of and that could in the crust that could indicate anisotropy fabrics and so on. How the rift sort of follows these directions as well. So these are deep indications of much deeper anisotropy than the foliation that you can map at the surface. So they indicate that there is something deeper going on here. It's not just a near surface sort of foliation thing. So clearly there's a rift again, extension direction and everything. Clearly there's an influence. And if we go into this rift in some detail, I don't remember exactly where it is. For example, some place in this rift. I can't put it exactly where it is on this map right now. But then, so this is a graben. And look at the margin of this graben. It's in Kenya somewhere. And look at how zigzag the geometry is. And why is that? This is a close up here, because it follows to the north. The northwest trend follows foliation in the basement. The basement is on the right side here, right? And these are the sediments, right? Oops. Sediments, rivers. It's happening all the time, like this, flowing into the basin, a big fan system. And then these are joints or fractures, faults, pre-rift faults, fractures. And then, you know, instead of just making a straight fault like this, the rift faults decided, because of the anisotropy, to follow these two trends irregularly and form this zigzag pattern. It's very impressive how that's actually formed there. Sometimes that happens, sometimes it's less clear that there's an influence like this, but this is a nice example. So that's foliation and fractures influencing rift fault geometry. Here's another example, and there's a seismic line, goes down to deep into the basement. It's from the margin of the North Sea rift. And you can see it's outlined in red here, folds, very significant folds. These folds are pre-rift. They actually formed, and this is from a paper by Johannes Wiest and others, including myself, during the extensional collapse of the Caledonian orogeny, where you have had extension as well, and you had sort of ductile basement moving up and being folded because temperature was going up, things were getting soft, we had extension, we formed these folds. And on the flank of these folds, like you can see the foliation of the seismic here, you get some faults developing very parallel to that fabric. So we can see this now on seismic data. And this is a map view of the same fold. You see the fold pattern. It's not a map, it's a horizontal slice through the seismic. The fold very nicely with parasitic faults and things. And then the fault is this yellow line here. And then it comes back here. Oops. It's a little inaccurate like that. So it's actually a little bit like what we saw here from the East African rift, but it's related to ductile folding and the way that the folding varies the orientation of the anisotropy of the foliation and shear zones, pre-rift shear zones, has an influence on how the faults evolve, where they form, and their direction, their orientation. And while we talk about that, which I also want to point out the importance of transfer zones, a rift segmentation. And the East African rift is a good example. That's where they were first properly described. It's not just a continuous rift. There's lots and lots of different segments that are linked together. And each of these segments have different structural geometries, right? So if you make a section through here, through this rift here, for example, you see a half graben like this. Here you get a very different, more wide with a horse in the middle. Go up here, for example, you have the mirror image of that half graben. The main fault is now on the other side, and so on. So these are related to variations in geometry along the rift. Famous structures, and there's quite nice drawing from an old paper by Erbinger, 1989, showing a little bit of that, sort of an example of a transfer zone in 3 dimensions, where there's this horst, for example, here that separates, in this case, the two rifts, the two graben on each side. And there are many different ways that you can put these faults, main faults together and produce things. There's a very simple one. What's meant by a transfer zone, a single transfer fault in this case, which is not always the case. It could be much more a diffuse linkage between the two faults. But there are two faults that are linked, and one is developing here on this part, and then the other one simultaneously up here. And the displacement on each of these is transferred between them along the transfer faults. And this figure here on the right shows some different examples of transfer. So this being a rift here, right? So rift here. But this, with these faults doing that, you get very different sections as you make sections across this rift. The structure varies along the rift. And maybe basement structures actually influence, in many cases, the location and occurrences of these transfer zones. Let's go to Brazil again and look at just that. There's this very fascinating failed rift from the rifting of the Atlantic margin, or what became the Atlantic margin, is this rift system here, the Concavo, Tucano, Jatobá basins as names, but there's one rift system, this whole thing. And if you look at that, you can see there's a one main fault down here, for example, right? Down throwing to the west, but that sort of disappears here, and then you get another the main fault now on the other side, and it throws to the east, and there's another segment down here, the Concavo segment. So there's a marked change from here basically to here, where there's this flip in polarity from depocenter here and depocenter there. Let's look at the depocenters. There's a 3D figure here, but this map may be even clearer. So we recognize these two faults that we were talking about. This one is here, and the other one is here. And you can see how the depocenter in blue, this is the gravity map, but it reflects the depth of the basement. So there's a depocenter here. That segment on the left side, the west side, and then the depocenter, another one reappears or appears here on the east side, and then you have another one here with the main fault here. So this changes all the time, and the transfer zone that I want to point to here is this one, Vaza-Barres transfer zone, that is kind of a diffuse zone, but still quite well defined at this scale, that lines up with the Sergipano orogenic belt that is located here. So then if we go in here and measure smaller scale structures that could tell us the direction of extension in this basin, which is published in paper by Peralta Gomez and others, myself and Renato Almeida, and some more, then the extension direction is like this, right? That means it's not perpendicular to the rift, right? It's not like that. Nope. It's like this is if we transfer that, and that's interesting because. So why is the rift north-south here in the south? Well, that's probably because of the pre-existing basement fabric here being north-south. And why is it almost east-west up here? That's because the basement orientation changed completely from north-south to almost east-west. And then there is this belt here in between that created the transfer zone. Let's see here. There's that rift again with some basement structures highlighted. So the rift is mostly north-south, like this. And it's just completely fascinating how it changes orientation once it gets up to the east-west fabrics, Pernambuco shear zone. And down here we have north-south fabrics dominating, so that's why it's north-south oriented, even though the extension direction is like this, right? If you have an extension direction like this, it's supposed to be arrows, then you would think that the faults would form, you know, something like this. Okay, these are the fault strikes, but they didn't. They formed no, oblique to the extension direction, and it seems, and that's because of the pre-existing fabrics. So pre-existing structures control the orientation of the rift, oblique to the extension direction, and created transfer zones across which the structure of the rift changed significantly. Go to the North Sea, back to these again. Talked about this domino system here. These are west-facing faults, left-facing faults. And then here in the other section, these are mostly east-facing, right-facing faults. And that happens across a transfer zone. So if I just quickly show this map, this style here with west-facing faults is, these are the faults here. This was the Irrgarden fault and the Vette fault we talked about. It's all west-facing faults, dominated by that. But this section here is farther north, so there's a lot of east-facing faults here, and then we get smaller faults here. So the transfer zone. Transfer zone in this case, it's between these two lines. It's something like this here, where the geometry of the rift changes dramatically. Okay, so now we got to the way that big faults grow. How do you grow big faults? We talked about that already, that small faults can grow into bigger faults. How exactly does that happen? And then again, we can look at experiments. It's always fun to look at experiments and see how faults, some small incipient faults here, how they start to grow and interact, and there's a linkage. So this is fault linkage thing. There's actually much better drawings here on the right. So these two faults now link up right here, and small displacement in the linkage zone that grows, and then you end up farther down here with a fairly big fault, but the irregularities along it tells us that it has a complicated history of linkage. So it's not with faults, they don't, for the most part, they don't grow so much from small faults propagating in all directions to become big faults, but to much larger extent, they link up individual small faults. So look at all these small faults up here. There's one there, and so on. All of these, they connect and form a much longer fault just by connecting and linking up. So that's called fault linkage. And just so we can look at this again. This is another experiment, plaster experiment. We're looking from above down into a box that is filled with plaster that is sort of it's quite soft. It is not liquid, but it's strong enough to form faults. And let's see. So that's that same experiment that we showed here, just to see how it plays out. Oops, why didn't that work? Didn't play. Something happened to this file. Sorry, but it would show. We'll see. It would show exactly this that we see here, how these link up and form. So here we have this system here, right? This fault here forms, and then there's a new one starting in the front. We talked about these faults not being active completely at the same time. That is forming here from, and you can see this zigzag thing here, and a little one here. and another one here, and so on. And they grow. You see the length of this one, for example, it doesn't grow very much longer. And then they link up. And when they link up, they form something called a relay ramp. And it's a very interesting structure that forms and become destroyed. There's another one here. So here, for example, and here. And there was one here back, it's just connected here. And that's quite an interesting, well, here's maybe the experiment. No, still doesn't work. No, that's what we had. But these are the relay ramps here, right? Why are they called relay ramps? Because there's a dip here that you don't find in the surrounding rocks. And here's an example from the field. This is from what's called the Grabens in the Canyonlands National Park in Utah, the USA, where we see ramp right here. And these layers are dipping down in this direction. There's another ramp here dipping down in that direction and fault here. So if we go down on the ground, it looks like this, the fault on that side. So that fault one is the fault that is here. And there's a fault here. There's a graben here. And then there's a fault like doing this. That's sort of the way it is. Oops, that followed us. Okay. So we can see the fault, it loses displacement and bleeds out up here, and the fault 2 takes over the displacement. And in between is this twisted or bent part of the stratigraphy. And the figure on the right here shows this evolution that we looked at in the experiments, where the two faults sort of overlap, grow past each other, they interfere, the stress field and the strain field, and eventually they connect and form a fault. And this fault is not straight, it has an undulation that could tell you that something was going on here in terms of linkage, just from that abrupt change in strike. And that's important for petroleum geology. I have to talk about petroleum geology too, right? So when you form this, as long as it's a ramp, then fluids can flow up this ramp quite easily. When it's cut by some fault, small faults, then in the beginning, this fault will be small, so it will still be more communication across this ramp, until at some point it will grow bigger. So these are important structures to know about and to look for when you map in rifts and similar areas. And they link up not only in map view, but also in the vertical direction. So that's important to note. Just an example from this is also from Utah. What we see here, there is a change in color, or so the different rocks on this side and this reddish sandstone on the other side here. So there's a fault here. Let me put the faults on like this. So this is an example where a fault is not a single fault, but it's a complicated structure, complicated zone of many fault segments. And if we look at this one here, that's, as you may suspect, I had the one there already, okay. It's a ramp, very similar to the one we saw. And this is actually the path. You can see the path here. So every year, this is in Arches National Park, there are about 500,000 people walking up this ramp to see the delicate arch that some of you may have, this sort of rock structure that looks like this, right? It's here. And people behave just like the road is here, just like fluids. They would choose the easy way up, right? Not climb the faults, that's hard, but follow the ramp. And that's exactly what fluids do in a reservoir. So being able to detect these zones, these locations, these ramps, is important. And using bend in the fault interpretation is a good place to start, a good way, something to look for. And we see these everywhere. These are my shoes here, and you can see the individual segments that will in the pavement here that will grow together into a more continuous fault zone, very similar to the one that we have here in arches over time. Here's an example from seismic interpretation, a paper by Jackson and Rotevatn, from what I remember, where we have these faults at the relatively large scale, 100-meter faults or something, and you can see depot centers, right, related to these faults. So again, in terms of deposition, it's very important to understand how fault systems develop. We're getting close to the end. Large faults, we have talked about large faults, and they are very important for many reasons. And in terms of petroleum geology, the first thing to think about is that they can create structural traps. They can store oil and gas. They can create these traps where sandstones are cut off and covered by cap rocks, post rifts, and being filled by oil and gas because these layers have been rotated during the faulting. So that rotation is actually very important for creating traps. And source rocks could be this thing here, for example, or something deeper down. So that's good to have these large faults. And then small faults, they are more problematic to engineers and production people because they can affect the reservoir performance during production. And just a few words about that before we end. One important thing that not everybody is aware of is the faults are complicated structures. They are not planes. They are tabular. Tabular structures means that they have a width or a volume in 3D, and that these complications change along strike and along dip, like these two faults here, right? There's not one fault, there are two faults. But down here, there's one fault. So this one, for example, splits up into two fault strands. It's the same fault. And changes a lot of things just because of that. So it makes a big difference whether you look at the fault there or there. Faults, and that's a simple fault. Faults are very complicated if they are allowed to develop. And depending on a lot of things, you can end up with lenses in the fault core with damage zone around it, lateral variations as shown in this figure, or maybe more of a fault zone that with individual faults or fault strands interact or link up in different ways along strike and dip. And on top of that, there is this thing about drag that we're not going to talk about, but that's also important in terms of communication. Yes. So from seismic data, you can see some of these complications, but not really the smaller details. So we need to use knowledge acquired from field works, experiments, and numerical experiments. So on a seismic section, a fault is often portrayed by a line, but the fault is, like we now understand, is much more exciting than that. And this nice picture that I stole from the fault analysis group in Ireland, John Walsh is here, I think, illustrates that. So this line is now at this level of resolution a much more complicated zone, right? It's bound by maybe these faults here, but internally there's a lot of structures and things and rotated layers. This black coal-rich layer is rotated down like this. The smearing is starting here. So it's complicated, and it depends on the lithology, deformation depth, and so on. Here I put this picture into the seismic line that I showed, this one here, this magnifying it a little bit. So of course you don't see this on seismic data. These are small scale features, but they are really important, can be really important for understanding communication in a reservoir. Some very simple experiments again. This is from University of Aachen. And there is a sand clay sequence that is being deformed by a fault that is forced across the model. It will propagate from down here where there is a pre-existing structure. And we get this kind of deformation is actually more of a shear zone than a fault, but that's what faults are. They also involve ductile deformation. So this the clay layers here, like this one, is dragged into a much thinner layer along the fault, right? So this is smear, and it smears so that this sand layer here, which should be in contact with this sand layer from the offset, because they are just aligned, right? It's that communication is cut off by this continuous clay smear. And same down here with the other ones. They can get very thin and develop on top of each other to add to the sealing properties, efficiency of the fault structure. And we see this in the field. Of course, this is a shaly layer here, and that is smeared down along the fault more or less continuously. And that's a very important thing. So then we get to what happens across the fault. And in very simple terms, there is different kinds of smear here. There or the communication and sealing terminology too. So the sandstones are yellow and orange here. The reservoir rock and the green are sort of impermeable non-reservoir rocks that could potentially smear out. So we have, for example, here we have what's called a juxtaposition seal. There's no reservoir on the other side, so there's no flow from one side to the other there. That's pretty clear. Then we have the second one here. What is that? Self-juxtaposed seal. That means that the sand reservoir is juxtaposed against itself. It's in contact with itself across the fault. So you would normally think that there would be flow here, right, from one side to the other. So what could hinder that flow would be the crushing of sand grains, in this case, along the fault rock itself. And there's a whole science around that, how you form different fault rocks at different conditions, depending on the sandstone, the burial depth, crushing of grains, cementation, and so on. But it's fairly likely that there is some communication across here in most cases, but not necessarily. It has to be investigated. Shale smear seal is this number 3. You see the green one is smeared down like we saw in the experiment. So the sandstone here, the orange sandstone here on this side, there's no communication across this fault if the seal is continuous, which is another factor to be considered. So there's all these kind of formulas you can use to estimate the likelihood of this fault being sealing, depending on the thickness of this green layer and so on. And displacement of the fault, those are the 2 main factors. But that's a sealing, or this is a shale smear seal that is considered to be a good seal in most cases, if there is enough shale involved. And these things will change. This is just to remind ourselves that the fault changes displacement along strike and dip. So this kind of contact relations that we look at here, what is in contact with what, and what is smeared, how far has this layer been offset, or likely is smearing to be continuous, has to do with where we are on the fault. It will vary along and across, and along laterally and vertically along the fault. And then there is the complexities. We'll go back to this one. There's a nice example, a very simple example, because there's one fault, there's 2 fault strands here. If we consider that, it would be possible, right? If this is our reservoir rock here, then it will be in contact with itself, self-juxtaposed all across this fault, because we have 2 fault segments, 2 fault strands. We will have communication like that. Fluids would flow like that. If we Photoshop this fault and imagine that the fault was a single strand fault, then that would not work. There would be no self-juxtaposition here, and there will be no communication in 2D here at this section, at least, from the foot wall to the hanging wall side of that layer. Okay. So that shows how important it is to actually describe and to know the anatomy and the geometry of this fault, what it actually consists of, which is extremely difficult in most cases because many of these are of subseismic character. So there is a large uncertainty about fault communication that has to do with this, and this is shown very nicely in a paper by Chris Wibberley from and others, 2008, very simple. And this is seismic data, right? That you don't see details, so you don't know if it's a single fault, no communication of the self-juxtaposition, or if it's a fault zone. And then what we haven't talked about, but is also important, is fault drag that could be of subseismic character and provide communication from one side to the other, even if the offset that you see on seismic data, which is this, is too big is bigger than the thickness of the reservoir. And then you can go down in even smaller details and consider what's called deformation bands and fractures and small-scale slip surfaces and so on, which are smaller, so small that you don't really see them, definitely not on seismic data. And they also extend beyond the tip of the seismically resolvable faults. And there's a lot of things that I could say about that, but I'm not. We're almost through here, both in terms of number of slides and time. So, but the way they develop and the way they form, the way they are distributed in a reservoir can be important depending on their properties. And the properties of these things, here's an example of deformation beds in sandstone. Again, a Brazilian example. This is from the Rio do Peixe basin, and for a relatively small fault here. And this is the even smaller scale deformation structures that you would, of course, not see in seismic data. Going very close, this is the Nubian sandstone in Egypt. Egypt, it doesn't matter, they look similar in many places. Sandstone with its porosity, and this is the deformation band, and this is about 1 millimeter wide. Looking at that in the thin section, we see that the blue colored porosity is almost gone within the band. So these are fluid, these are permeability reducing structures. And just in the field, you can pour water on one side and you see it will have some problems. The water will have some problem getting through this deformation band. This is a deformation band here. This fluid is diverted like that, which is very different from fractures. And this is a small joint, basically, fracture here. And you can see from the decolorization of the red sandstone that fluids must have been flowing along within the fracture. They don't do that in deformation bands because deformation bands are less porous and permeable than their host rock. So these things have to be taken into consideration. And again, that's a big topic that we're just scratching the surface of in this presentation. So I actually stop here at these very small scale deformation features. You have to take everything into consideration, from the largest faults to the smallest structures, if you want to do a proper job as a petroleum geologist. So that's a few points in the end. If we want to understand rifts or extensional basins with or without petroleum, it doesn't matter. It's even if we don't care about petroleum, we need to study their evolution through time. We have to explore their geologic record preserved in abandoned rifts that we can see and explore, and compare different types of rifts that terminated at different stages. We use physical and numerical modeling and of course, any information that we can get about rifts. At different scales, like I said, it's important to look at these things at the different scales, from the entire crust and lithosphere down to the smallest deformation bands and grain deformation features and cementation, which we didn't really talk about. So that's an important point. Large faults are trap-forming features, as we pointed out, but faults in general are complex structures with features and characteristics that may vary rapidly along strike and dip, and these are very difficult to predict, but it's still good to know the possibilities and see examples, which you can see a lot of in the field and not so many of from seismic data. And this figure here that is on the right is one that sort of illustrates some of the complications that you may have in faulted extended regions in terms of, you can see smearing here. I'm not going to go through all of this fault zone complications along faults that change character, along faults, the ramps that we talked about. The ramps are here, this is a broken ramp, and so on. And subseismic structures that are not even in this figure may give production surprises that you want to be prepared for. So don't forget about them too. So by that, I'll come to the end. And this has been a very sort of long journey through rifts and extensional deformation structures as kind of an overview. And hopefully you learned something new about something that you can explore in more detail. There are many resources in books and online that are useful for that. So by that, I will just say thank you for your attention, and maybe there are some questions. Let's see. Get out of this. There we go.
So, hello everyone. As Vinicius Rigetti said, what a nice presentation. Thank you very much for this incredible talk, really. We appreciate the way you take care of the students, not only the students of the University of Bergen, but all the students, like with talks like this, with your books, with everything, really. As people were saying on the chat, I can say that we consider you the father of the structural geology, because you are able like to untie this content that is very, very, very hard, like mainly for the students. For me too, I can say for me that it's really hard, but I just have to say thank you very much for this opportunity, really.
Oh, that's too much, but yeah, it was fun. Thanks again for inviting.
Thank you. We had people from a lot of countries. Gabriel is showing here the screen. Yes, a lot of people like here greeting you, and yes, we have something important to say about some lectures that we are going to present. I'd like to ask Gabriel, please, to show on the screen some lectures. Unfortunately, this lecture is going to happen in Portuguese, so let me just present in Portuguese. A APG da UFRJ vai estar apresentando, gente, amanhã, no canal do Twitch deles, esse webinar, né, Status Atual Exploratório das Bacias Marinhas Brasileiras, com o profissional Guilherme Arruda, da Repsol. É um profissional muito bom, e a gente indica muito, né, a nossa irmã, nosso capítulo irmã, e o link está aqui embaixo, tá? É só acessar amanhã às 18 horas, tá bom? E nós teremos também uma próxima palestra nossa, que vai ser com o profissional João Paulo Salazar, né? Ele é geólogo pela Shell. A palestra vai ser uma introdução a sistemas petrolíferos, né? Nós já assistimos um pouco de sistemas petrolíferos hoje com o Fossen, né? Essa palestra vai ocorrer no dia 1 de junho, às 18 horas, né? Pelo horário de Brasília, no nosso canal do YouTube aqui mesmo. I was saying that this guy here, I don't know if you understood, but this guy, he's a geologist from Shell, and he's going to present like an introduction of petroleum systems that you have like just talked a little bit about, and it's great for everyone to understand. And so let's go to the questions. We have some questions here for you. Let me see if Gabriel can put this on the screen. Yes, the first one was German asked, Professor Fossen, do you have any study where you measure the fault spacing, bed thickness, radial, and how these values are statically distributed?
Yes, I have not done that systematically myself, but there are a few studies. I don't remember the references. They are referenced. There's the one by Soliva and co-authors, Soliva from University of Montpellier from 2000 and was that 13? I don't remember. It's in its list. I don't have the reference, complete reference, but it's mentioned in the text in the presentation somewhere. So that's one. He looked at small scale, sort of centimeter, decimeter, meter scale beds, basically, or different mechanical properties. And then there are others that have looked at rifts, large first order rift faults and things, and I don't remember the references, but they are referenced in my review paper on relay ramps in Earth Science Review from a few years ago with Atle Rotevatn. So if you find that, you can find all my publications on my website. Actually, you can download them from there if you're interested. So there are some references in there. I can't give you more precise references right now, but some people have looked at that. Just a matter of searching.
That's great. Maybe Jeremy, you can send it as a mail with this question, and then we can send the references.
Yep.
Right. So the next one is Misael Felix asked, thanks for sharing your knowledge, Fossen. Could you make some comments about the formation of oceanic crust and its relationship with transform faults and fracture zones?
Yeah, that's an interesting question. So, to what extent do continental transform faults that form during rifting relate to the fracture zones, right? In the oceanic rift system? And it's clear that from experiments and some observations that you can form fracture zones that are completely independent of the rift transfer zones in ocean. Once the ocean starts to form, they can sort of spontaneously form without any relation to the continental transfer zones. But then there are the big transfer zones that we see form very nice often some shared sort of strike slip continental margins. So along the margins, and some of them continuous fracture zones. So there is both, but it's not easy to. It's a very good question, and good questions are often difficult to answer, at least in brief. But there is some relationship, but not all transform faults relate to rift or transfer structures at the continental stage. But some of them seem to do. I think that's all I can say now without digging a little bit into the literature. There are quite a few papers on that.
That's awesome. Thank you. We have some more. Rafael Quintana Gomez, he said, hello, Professor Fossen. Thank you very much for this presentation. You have been talking about sealing faults because of the smear in extension structures. Does this work similarly in thrusting?
Yeah, that's a good question. Definitely, there is smearing. You can see smearing in thrust faults as well. I have pictures of that, and I didn't show them today. But I have not seen. I can't remember having seen a comparison between, because it's there is a database or lots of observations from rifts and rift-related faults, and they built this database and this relationship between the thickness of the smearing layers, the clays and shales, and the amount of displacement on the fault, and they found sort of relationship there that correlates with the sort of the probability of the fault being sealing, the smear being continuous. But that's all from extensional faults as far as I remember. I don't remember having seen similar studies from reverse faults from contractional settings. Maybe that exists in some oil company, but that has not been published, or maybe I have missed it. If someone has information about that, that would actually be quite interesting. So, but there's much less data published on reverse thrusting, reverse faults, and smearing.
All right. So thank you. Let me see if we have some more. Mariana Maria Rezende said, "Thank you for the lecture, Mr. Fossen. I live in northeast of Brazil, and it's very nice to study geology with structure here. How geophysics and petrology can help me to describe transitional basins?"
Yeah, this transitional basins, I guess by that you mean transitions from different segments of the rift, different parts of the rift where structures are different. And geophysics, yeah, definitely can give, there's different kinds of geophysical data that, of course, seismic data is very important, but also gravity. I showed some examples of a gravity map, at least, showing in depth, the deepest parts of the basin, the shallower parts from the Bouguer anomaly map. And there are magnetic maps that show similar things. Some of these are actually available online for the basins, the Cretaceous basins and Jurassic up in the Borborema in the northeast of Brazil. So there is actually quite a bit of information there available. And so that's definitely very important when it comes to magnetic and gravity data, to see where the basin is deep and shallow and how that changes from one part of the rift to another part of the rift. And then in between, you have to have some sort of boundary transfer, domain boundary, whatever you want to call them. Yeah, petrology, this, I'm not sure about petrol, but sedimentology too, depositional patterns, these are controlled by where you have sort of the deep part of the basin, shallow parts, and migration, where the routing system of sediments, is controlled by the transfer zones being oftentimes higher than the basins on each side. So if you look at you can go either way. If you look at the pattern of deposition, if you can work that out, then that might tell you something about where you have these transfer zones. Or if you know where you have transfer zones, you can predict something about the depositional patterns of the sediments and the type of rocks and the distribution of rocks and petrology, where you have more feldspar or whatever. I think that's what I can say right now about that.
That's awesome. Thank you. So we separated two more questions. So one of them was Felipe's. He said, "Amazing presentation, Professor. Do you think that much of the source rock formations of the world are rift related?" Felipe Vargas, Sierra Cole. Thanks.
Yes, there's a lot of, in source rocks in rifts are usually rift related. There's, as far as I know, that's forming during rifting or even after rifting, just after rifting. In the North Sea rift, for example, it's interesting, the source rock formed after the reservoir rock, but then you had these faults that put the source rock in contact with the reservoir rock, so it flowed from the source rock, which was just late rift to post rift, and into the reservoir, very late rift stage, I guess. But in general, yes, I think, like I said, there is more than 50% of the reservoir rocks or the oil and gas resources are found in rifts and rifted margins. So for that, just from that, much of the source rock are also rift related. Yes, to make it that short.
That's great. And the last one was Andre Muhaisen. He said, "Professor Fossen, I give all greetings, possible for this presentation. You're indeed the father of the structural geology. Could you give more examples, rift-related, petroleum basins around the planet?
Yeah, how many more hours do we have? Yeah, I mostly focused on two that I know, a couple that I know fairly well. The North Sea I know very well, and I'm starting to get familiar with some of the Brazilian examples too. And of course, there's a lot of rifts and a lot of examples from around the world. And the map that I showed as one of the first slides shows exactly that, shows the distribution of rifts and rifted margins where the rifts have been pacified, right? So you have to go back to that map. I think and it shows a lot. And of course, a lot of it has to do with the breakup of Pangaea and the formation of rifts between South America and Africa and North America and Europe and so on. So there's a very significant history of rifting there.
Yes. So thank you very much. A lot of people greeting you and congratulations. And so we'd like to ask you to say just a little bit more because we'd like to talk to you. And I'd like to say thank you for everyone that watched us. It was like more than 100 people all the time watching us, like between 100 and 200 people watching, and people commenting all the time, people thanking, people all. It was amazing, really. Thank you very much for the opportunity. So we're going to stop the live and let me ask Gabriel here to show you some comments. That's awesome.
No, Brazilian coffee.